It doesn't look like it.
Well, there's a bit of a smile there, come on. So I mean, I have to give you some motivation as to why this has been like a 10-year research project on Noether's theorem, and certain pictures are just so beautiful that they're worth looking at and meditating on. Obviously, Noether's theorem it gives you Kepler's laws, and to me, one of the things that I find most amazing about Noether's theorem is this sort of central mystery, which is that you have a physical principle given by an action principle, by least action principle, and the law comes from the fact that certain mathematical the fact that certain invariances under the mathematical formulation of that principle don't matter. And so, for example, you can shift time, you can rotate space, you can do all kinds of things depending on the geometry of your problem, and these give you these sort of seemingly irrelevant things to do with the mathematics rather than the mathematical coordinates, if you like, rather than the description, rather than the physics, actually give you such physically relevant laws like conservation of energy, momentum, and angular momentum. And that to me is quite mysterious. So, so anyway, and here's another beautiful picture, and I don't know whether it's upside down or from a different hemisphere, but yes. Well, so one of them, Venus is tracking across the bottom, and Venus is tracking across the top. So anyway. I don't care. It's very beautiful. So this was my initial motivation, was that I was in conversation with Ian Ralston, who at the time was at the Met Office, the UK Met Office, and they had famously failed to predict a hurricane in 1987. And they sent their best mathematicians to a think tank in Europe. This is the story as Ian told it to me. I wasn't there. Famously failed to predict this hurricane. They sent their best mathematicians to a think tank, and the answer came back that the numerical simulators had not properly tracked or conserved potential vorticity, and this was the problem with their predictions. And so but of course I knew that we had certain no-go theorems in numerical analysis. You couldn't have that and that. You couldn't have the symplectic structure, the variational structure, and conserve energy. And I felt that while these theorems were mathematically proven, nevertheless they were philosophically, and I'll explain myself in due course, philosophically wrong. But you should be able to have whatever you want, provided you know where to look. So this was kind of my motivation. So in this talk, I'm first going to look at the smooth case, and the first thing we're going to do is expose the structure of the equations and the laws in terms of the invariance and the frame, and you'll see why this is a good thing to have done. So basically, the big problem with Noether's law in the smooth case is expression swell. And then I'm looking at the discrete case. So I'm looking to embed the physics via the least symmetry into the numerics, and I'll explain myself properly with that. It turns out that the finite difference case and the smooth case look like examples of the same theory, provided you look at them through the correct prism. And I'll tell you what that prism is. The finite element case, I've had 2 goes at this one, and this has a very different look and feel indeed. It's very different. The second attempt has been tested numerically, and it does look very different. So I did this second attempt at Noether's theorem for finite element with Tristan Pryor, who's moving from Reading to Bath, and so anyway. And I'll show you a simulation at the end. So here's my running example that you've now seen in my previous two lectures, and I hope you remember it. So this is the projective action of SL2. So we have 2 by 2 determinant 1 matrices. We have the projective action, and via the chain rule, as before, we induce an action on all of the derivative terms. And as before, we have this lowest order invariant called the Schwarzian derivative, which looks like this. So this is a very famous invariant. So all right, supposing our Lagrangian is our Schwarzian derivative squared plus half the Schwarzian derivative, no, the second derivative of the Schwarzian derivative squared plus half times the Schwarzian derivative squared. I just made this up. I just made it up to prove a point. I made it up to prove a point. This is invariant, so this Lagrangian is, so remember x is invariant and the action's all on the u. This is invariant under the induced action of SL2 by construction. And by Noether's theorem, we have 3 first integrals, 1 for each dimension of SL2. So we have 1 for the variable a, which is the scaling variable. We have 1 for the varying b, which is the translation variable, and 1 for the variable c, which is the projective action variable. Alrighty, so let's look at one of Noether's laws. Oh yes, so you can tell because this baby has degree 3, then that has degree 5, and so the Euler-Lagrange equation has order 10. Order 10, yeah. So I get 3 first integrals, and they're of order 9, and here it is. Ta-da! So, I don't know, is there anybody in the world who can do anything with that at all other than differentiate it and work out that you get your Euler-Lagrange equation times a factor? And if you look, and it doesn't matter that it's not quite in focus because you can't do anything with it anyway, but if you look at this one here, that actually has 9 ones if your eyesight's good enough and you don't go around like that. So that wasn't, so this is not useful. And this is the problem with expressions as well. You get expressions, you get things which are mathematically true but essentially useless. All right, so we're going to use the power of the moving frame, the Lie group-based moving frame, to derive Euler-Lagrange equations and conservation laws in which the structure of those laws and equations become evident. That's what we're going to do. So we're going to replace wallpaper with structure. That's the aim. So I think this was first done by Irina Kogan and Peter Olver, and they have results in terms of a tri-variational complex. My methods are much more native. They're much more calculus-based, and they're much more native to the symbolic calculus of invariance that I've shown you a little bit with. So the general case is in this paper here, and this is my textbook, and this was what I'm going to show you appears in here. So let's remember we have this is our projective action, and what I'm going to do is I'm going to introduce a dummy variable, t, a time derivative, and again I'm going to induce actions now on the time derivatives like this, all of them, and why am I doing that? I want to take advantage of this very powerful symbolic calculus of variations, symbolic calculus of invariance, which doesn't actually include a Frechet derivative, but it does include ordinary derivatives. And if you do this, and you consider the variation v to be du by dt, then you get the same symbolic result. So I only care about, because I'm doing a symbolic computation, I only care about the symbolic result. And I'm taking advantage of the fact that I can do that. Alrighty, so now, as we saw in the first lecture, I think, or the second, that I now have a new lowest order invariant, which is ut over ux. And so this invariant doublet is my invariantized variation. Now remember, I've got a Lagrangian which is invariant under a certain Lie group action, so there's no point taking variations in the direction of the Lie group action, because it automatically stays invariant. There's only the point to take variations in opposite directions. So, and this is kind of why this works, that I can invariantize and then do my calculus of variations. That's why it works. But anyway, remember that if I differentiate this with respect to x 3 times, and I differentiate this one with respect to t once, I get uxxxt over ux cancelling, and the result is this. This is the differential identity or syzygy between these two invariants. So I've had a question about this word syzygy, which seems very mysterious, but I think it's wonderful because there's no vowels. Good for Scrabble. So what this syzygy means, if I back substitute this for v and this for w, it all goes, you get 0 equals 0. So this is an identity, and syzygy comes from the Greek, meaning intertwining, and I think its modern usage is more to do with your wife. Yes. So so these two are married somehow, and that's their marriage vow, that's their identity. Yeah, so there you think of it like that. Okay, anyway, you have to remember this syzygy because it plays a key role.
They divorced or?
No, they're not. No, but yeah, well. Alrighty, so let's have a look at what the calculus, well, what the method for finding the Euler-Lagrange equation looks like in terms of my invariance. So it's almost the same. Here is my Lagrangian, and this all only depends on x, excepting that I now have that u implicitly depends on t, and I assume that everything is beautiful enough that I can differentiate under the integral sign, and I do that. I then do my standard integration by parts to get rid of all of these operators in here. So I take this out to the other side, and that's called evil. See, that is the Euler-Lagrange operator with respect to my invariant v. So if this was a Lagrangian for v, that would be my Euler-Lagrange equation, but it's not. I need the Euler-Lagrange equation with respect to u. So far I've got the Euler-Lagrange expression with respect to v, and then my d by dt of v is of course my operator h acting on w. And w is my variation, and h is always a linear operator.
What is it equal to 0, or is that now just?
No, I'm looking for the extremals.
Okay.
So that equals 0 means is the extremal calculation. Yeah. There's another equals 0 for invariance, but this is not it. Yes. So this is always a linear operator, so I can take the adjoint. So now I have, and I get boundary terms, of course. And these boundary terms is, of course, Noether's theorem. So here I've got this adjoint acting on here. W is my invariantized variation, and so this thing being 0 is my Euler-Lagrange equation. Now, here's a little theorem that you need to know. If your Lagrangian is invariant under a Lie group action, then the Euler-Lagrange equation has that Lie group for a symmetry, and therefore I can write it in terms of invariance. So what I've done is I've written the Euler-Lagrange equation in terms of invariance, and the reason that is not equal to that is because there's a non-zero denominator, which in this case you'll see is 1 over u of x. Because I've done an invariantization. But or this is simply, you write that in terms of invariance, and that clears denominators. Okay, so for this particular syzygy operator, because it's a famous operator, it just so happens that it satisfies this. So what we've done is we've written a very complicated, messy expression that you really can't look at, and we've written it in terms of two operators which are well understood. So this is the structure of the Euler-Lagrange equation. Alrighty. So what about the laws? Well, the laws are not invariant. So you probably know that if you have a Hamiltonian system and there's a moment map, a Hamiltonian system with a symmetry, there's a moment map, and the moment map has an equivariance. It's a very famous theory about Hamiltonian systems. So these conservation laws are simply the higher order multi-dependent variable version, which is that they're equivariant. Noether's laws are equivariant, they're not invariant. And of course we know what equivariant things are, yes? They're frames. So let's look at this. So this was not derived by a theorem. It was derived by hand from looking at a variety of Lagrangians. And at some point I realized I always had this form. And I could write them, so they're my constants, my three constants of integration, and these is a column of invariance. Once I've solved my Euler-Lagrange equation for V, because the Euler-Lagrange equation is an equation for V, once I've solved for V, I know what those babies are. And then of course I looked at those, and I realized that I had this expression, and of course you might remember them from yesterday, yes? This is my standard moving frame. And at this point I was coming to the end of a book on moving frames, and it was a subtitle could be a symphony on or a symphony on actions of SL2, and of course I recognized these quantities straight away, and you may or may not remember that, but that is the adjoint action of the Lie group on its Lie algebra. So remember what that was. So you have a group. You have A x maps to A x A inverse. And because I have a 2 by 2 determinant of determinant 1, a 2 by 2 matrix of determinant 1, that is just simply, you're going to get something quadratic, and that's what you get. So, anyway, this was practically too good to be true. I could hardly believe it. I could hardly believe it. That was the inverse of the adjoint representation of a frame that I knew and loved and had just written a book on.
Is that a syzygy?
Maybe a synergy, I don't know.
Synchronicity?
Yes. So I knew it was too good to be true. There had to be a theorem, and then I just sat down and to prove the theorem. Yes? Yes. Okay, so of course, once you see something like this, you want to be able to, I've answered half of these questions. What representation yields that? It turns out that Noether's theorem found the frame without knowing any theory of moving frames. Yeah. So, but let's now look at this. It's the right so this is the right adjoint because I've written it as column vectors, representation of SL2. And once you've solved for V, if you look at this, I have three equations for U, Ux, and Uxx. So, of course, I showed you yesterday that once you've got V, you can find rho with a Lie group integrator, and from there you can find U. But here I've got three constants. So if I just do a little bit of differential elimination on my three equations for U, Ux, and Uxx, I get one first integral of my Euler-Lagrange equation, and this is because, where does that come from? It comes from the fact that this action of the group on its Lie algebra, where this is SL2, has an invariant. And that's the invariant of that action. And I also I can eliminate the second, I can eliminate the second derivative but not the first. If I look at this now, if I dump that V3, which is minus 2 EVL, into the deep independent variable of this ODE, then what I get is that the entire class of ODEs that come out of variation of this the entire class of variational problems with this symmetry come down to solving a constant coefficient Riccardi equation, which I think is quite interesting. Yeah. So we get, so obviously this was wonderful, and I worked on this with Tania Gonçalves, who's now in Brazil, and we had a very good time with it. All right. So just to remind you that this moving frame is an equivariant map from M to G. In this case, M is the jet space with those coordinates, G is the Lie group SL2. And just to remind you of what this equivariance means. So, and actually you can use this equivariance to simplify this. You can use the equivariance to reposition U and X, or just U, to simplify this, to simplify those constants. That turned out to be an important for other applications. All right. So, we do know about the theory of moving frames. Yeah, well, so Noether's theorem is calculated a moving frame without knowing any theory of such things because it's equivariant. And we use the moving frame theory to prove results. The simplest expression with no group action on the base space is you do get a divergence expression which is 0 on the Euler-Lagrange system, and you get this inverse adjoint acting on the front of all of your as many i's as you have independent variables. So that's the general, and the general result's a bit more complex, but I'm not going to write it down.
So the VI's are those you had in your examples?
Yeah, so I only had a V1 because I only had one independent variable, but you get one for each independent variable. You get a vector, and then and that's the structure. So this tells you the structure of the conservation law. You know the conservation law is a divergence expression, and that tells you it. Yeah. In general, the conservation law is actually an n-1 form, and then you have to work a bit harder. Yeah, but you can. Alrighty. So moving frames are wonderful. But we've talked about moving frames. All right. So now let's look at finite difference. And I want to convince you that these two theories are exactly the same theory, provided you look at it through the right pair of glasses. So let's have a look at the smooth. So first of all, we have integration by parts on the smooth. And on the right-hand side, the finite difference, we have summation by parts, which simply means that I can put the shift on the end. So if I imagine that shift of n, which just simply shifts the index up by 1, and I can move it to the other, so that the adjoint of the shift map is shift inverse. And then here I get a boundary term, and here I get a boundary term. Just the same. But the reason it looks the same is because I'm using shift and not shift minus the identity. Yes? So the right pair of glasses is to forget about shift minus identity and only care about shift. So the L2 adjoint of d by dx is minus d by dx. The L2 adjoint of the shift is shift inverse. The operator d by dx is a derivation, and the operator shift is a homomorphism like that. So even though everybody wants to do shift minus the identity and have these very elaborate expressions for their Euler-Lagrange equations in terms of shift minus identity, do not do it. Free yourself from the tyranny of shift minus the identity. And here's why. For a smooth Lagrangian of that form, the Euler-Lagrange equation is this. It's dl by the jth derivative, and then you put this minus d by dx to the power j in front of that and sum them up. The finite difference Euler-Lagrange equation, I do almost the same. I take the derivative with respect to the n plus jth, and most people throw away the n's and just put n to 0. But anyway, I've kept the n here, and then instead of this minus d by dx to the j, I have shift inverse to the j, and that's the Euler-Lagrange operator. And when you go through the formulae, when you actually consider the boundary terms that these operations give you, it's the same. You give me the smooth Noether law, I give you the shift. I give you the shift Noether law simply by replacing minus d by dx by shift inverse. And in fact, the finite difference is even easier because there's no action on the index. So there's no action on the discrete independent variable. So all of the complications to do with actions on the base space all disappear, and you're left with one theory being a syntax translation of the other, of a simpler version of the other theory. So anyway, many authors have discovered finite difference Noether laws with various degrees of bad notation, and the most general, and I can recommend this one by Lin Yupeng, and there's a very careful study here because if you read this paper you'll see it's actually really quite interesting. Anyway, so let's look at the world's simplest example, and this is T.D. Lee, who's a Nobel laureate, and I think that if it's good enough for a Nobel laureate in physics, it's good enough for me. So here's how he goes from the world's simplest example, from the smooth to the discrete. He does the standard approximation of dx by dt, and the only key point that I really want to point out is that this volume form, you have to discretize that as well. You have to put that in. And if you don't do that, you don't get the equivalent of conservation of energy. You don't get it. So that's really the key point of this slide. And I'll show you later that there's also a conserved symplectic form as well. So you get a conservation of energy and a conserved symplectic form if you pay attention to also discretize, if you don't throw that away. And in order to do that, he's also had to introduce essentially a moving mesh. So he's had to reintroduce the spatial variable, time and space variables as new dependent variables. All right. So for difference variational methods, we have similar results on the difference Noether theorem. And this is now 2 papers just appeared in Transactions, Maths and its Application. It's 80 pages to prove everything in mega detail for every order and lots of examples. And I'm going to show you one of the the example I think you'll be interested in. And it's but the moving frame in this paper was the one developed in these papers with myself and Gloria Mari-Beffa. So the discrete frame, as we saw yesterday, is essentially a sequence of frames, and here in the smooth case the invariants are the components of these matrices. So I've assumed that the independent variables here are invariant just for simplicity. There are equivalent matrices when they're not invariant. In the difference case, I have what's called the Moira-Cartan matrices, and the only thing that's new is I now have difference invariance and difference invariance and differential difference invariance coming from this matrix here, and I get one of these for every n. And here were the syzygies were the components of this matrix that I drew yesterday, and for the difference case, these are the syzygies that play a role in the proofs and the proofs of discrete Noether's law.
So the sub key is
d by dt. Yeah, absolutely. Yes, so that's why the t is upstairs there, because that's not a derivative. But that one is. Yes. So I wanted to show you a little, a nice example, which is Euler's Elastica. And some of you have seen this before, but I don't apologise because some people haven't, and besides, I love it. So the example concerns having a difference model of the smooth Euler Elastica, which is symplectic and has all 3 conservation laws built in, all 3. And in the sense that the discrete Euler equations and the laws all have the relevant smooth equations and laws as the continuum limit. And the group here is rotations and translations in the plane. And so the simple method, so I've had various ideas over the years, but this is a very simple idea, was simply to match the smooth, because the moving frame is at the heart of both theories. We have the moving frame, the syzygies on the moving frames give you the structure of the Euler-Lagrange equations, and the moving frame itself appears as a vital ingredient in the conservation laws themselves. And so my idea was, well, you're obviously going to get convergence if the moving frames converge. So that's the idea. So here is the picture I showed yesterday, or the day before yesterday. So in the green I have Cartan's frame. So remember we're doing rotation and translation in the plane. So Cartan's frame is simply this orthonormal thing coming along where E1 is the unit tangent vector, and the Lie group-based moving frame is translation to the origin of my point and rotation to the tangent being flat. So this is a right frame, has the right equivariance, and I've simply taken the matching thing as far as I could as for the discrete. So my discrete curve is I view as a series of points, and again I take the translation to the origin and the rotation so that that line segment is flat, and that's going to be, and that frame at the nth point is my nth frame. So remember, a discrete frame is a sequence of frames, so I need a sequence of normalization equations. Yeah? So that's what I've got. So what are the results for the smooth case? Well, that is the Lagrangian, the world famous Lagrangian, famously solved by Euler in 1746, and you still see papers in computer graphics that get this wrong. It's amazing. And it's been solved for 300 years or something, and almost 250 years. It's just amazing. They don't get that. They don't get the cube. But anyway, it's there. So anyway, that is the expression for curvature, and that is the expression for the arc length. And the laws look like this. So that is my vector of invariance, and this gives you the adjoint representation of my frame, the smooth frame. So this was studied in depth with Tanya Gonsalves. Okay, so if I put my additive row to the other side, then I have this, and it's quite clear that that's a rotation matrix because xs squared plus us squared is 1, because that's the definition of arc length, yes? That xs squared plus us squared is 1 is the definition of S. That defines the parameter S. So this is a rotation matrix, and that means that the norm of C1 and C2 is the same as this norm, so that gives me my first integral, which we all knew it anyway, but it's fun to see it coming out. And we also have a linear relation between x and u, and then you just simply have a single remaining ordinary differential equation to solve. So in other words, we've reduced the integration problem to algebra and a single quadrature. That's what we've got. So that's usually what the laws give you. Okay, so here's my two representations. So I just wanted to point out that that's the standard representation of the semi-direct product of this. This is the standard representation of the special Euclidean group on the plane. The right adjoint looks like this. It's got this kind of little twist to it. So if I drop in my frames into my right adjoint representations, so this is what I want to match. This is what appears in my conservation laws, and this is what I want to match. So there's that baby, so that the tan of theta s is this baby, and of course I have that squared as 1. And here is my adjoint representation of my the zeroth element in my sequence of moving frames, which is the discrete frame. And you can see that I've got tan of theta naught is this, which clearly matches that, and my L naught is that. So that's what you would expect. And so if I look at in the adjoint representation, my Moira-Cartan matrices, so this is the additive row S, additive row inverse. It looks like this. And so that is the generating curvature. And here, if I do the same thing here, and I want to match that to that, so I have to have that this is the identity plus delta S times that. That's what I want, because I want the continuum limit to work. Yeah, and I want to build in. So why am I doing this? I want to get everything for free once I've designed the Lagrangian. That's what we're aiming to do. So once you've got the Lagrangian with the correct continuum limit and the correct symmetries, then the idea is that you just go through with your discrete Euler-Lagrange operator and your discrete conservation laws and convergences for free. So that's what I'm trying to do. Right. So anyway, we do that, and if you take a first order approximation, and you can do more sophisticated things, but this is what we did. So that is my first order approximation. So that is the change in angle, and that is the length of the little edge. And ds is L0, which is what you'd expect. And so we consider our approximation of kappa squared ds to be that. So I square that and multiply by L0, because you have to keep the ds. Okay, so we go through it all and we do it. At least if you're Anna Rocker that I did this work with, you do it. She's there, just graduated. So and these are the difference laws now look like this. And we have a matching first integral, and we have a matching increment in the angle, and we have matching angle in terms of these invariants here, and we have a matching linear relation, so everything looks very nice. And we use a few little clever bobs and bibs to actually do it, and this is the result. So we're solving for the change in angle and the change in length, and the conservation laws can be evaluated at the initial data, and these were used to match the smooth to the discrete solution by matching those values of those conservation laws. And you can see that the initial data is the length includes the initial step length, and as the initial step length goes down, you can see I'm getting a better and better approximation. So those equations were quite hard to solve because they were very nonlinear, but since then my next student, Michaela Zadra, realized that if you put that L0 to be constant as a constraint with the Lagrange multiplier, then it's much more efficient. So you can actually do quite well on that. So this is a first step, and I make no claims for efficiency. It's just an in-principle thing that you can do it. Okay, so what price? So the Gay and Marsden theorem tells you that you cannot have a numerical integrator for a Hamiltonian system where all of the other symmetries other than energy have been divided out, and it then says that you cannot have a symplectic scheme and exactly conserve the smooth energy unless you're tracking the exact solution. However, you can have a conserved symplectic form and a discrete energy which has the correct convergence to it. So I think that's the land that I'm living in. So in other words, we want to make the discrete Lagrangian to be invariant under the induced action on the approximation data, have the correct continuum limit, and we want to write down exactly conserved discrete Noether's law, and then we need the discrete Euler-Lagrange equation and discrete conservation laws converge to the desired smooth equations in some useful sense. So that's the map of the landscape, and the idea is to guarantee that, and for the finite difference case, you can do it by matching the discrete, the frames. So all right. So when constructing a discrete Noether's theorem, for your approximation model, the big challenge is to find where the group action has gone to, and this is particularly relevant if your group action is translation in time and space and rotation in space, yes? Because that's an action on the base space, and if you it's quite clear that you've got a little bit of a problem. You can't move if the dots are fixed. But in fact, the Lie group action doesn't disappear. It just goes into your approximation data. So for finite difference, It just goes into the is simply the value of a point. So the induced action there is obvious. For finite elements where the approximation data takes the form of average values and moments, average values of various components of your functions and their moments over edges and faces, it's very easy to induce the Lie group action on things like that. And this does not rely on changing the element over which you are integrating. That is a bona fide Lie group action. It's not hard to that's not hard to prove. You have to, of course, you have to induce this, so you get this Jacobian coming out. So I worked on this finite element Noether theorem with Tristan Pryor. We published that. I do have an earlier version using Doug Arnold's complexes. It was never tested. I had this grand plan, you know, that he had this wonderful finite dimensional Hilbert complexes, and I was going to embed those in an exact sequence of the resembling the variational complex, and so I know a lot about homological algebra. I can really do that. And I did have a go at finding Noether's theorem using that framework. It was never tested, and the reason that this one with Tristan is so good, I think that should maybe be revisited by somebody who, I mean, maybe there's some value in that. But this one worked quite well because it turns out that if your action on your base space is linear, as it is with translation and rotation, then you can use out-of-the-box finite elements. So how much better would we do? How much better would we do with yours, Doug? Maybe, maybe you get something really nice, hey? That was the grand plan back then. You can see how long ago it was, and we know a lot more now, and maybe a better shot can be made at it. Okay, so remember that the link between extremization and Noether's laws starts with 2 equals 0. See how good your question was? We have a 0 equals at the extremal for this variation, and we have a 0 equals for this, and this for the variation in the direction of the group. And the idea is always to play off this with that. So in the smooth and the finite difference, we can use integration or summation by parts to actually get something that actually looks like a divergence. But in the finite element case, it's much weaker. We get a weak law in the functional analytic sense. And so we designed our Lagrangian, our discrete Lagrangian, to be in terms of the approximation data. And once again, we have 2 equal zeros. One at the extremal and one for the invariance, like that. And that's your starting point. And the story after that depends on your actual approximation data. Yeah. Okay, so for the standard finite element method, you will get an exact conservation law, and I say exact. It's the weaker the invariance in the functional analytic sense, the weaker the law. No symmetry conditions on the mesh are required. For symmetries that are linear actions on the base space, you can use ordinary elements. And because integration by parts is only valid piecewise, the laws have a very different look and feel, and in particular, they have a lot of summations of jump terms. Yeah. So I thought I would end the talk with a bit of fun. Emmy Noether never went to Stonehenge, as far as I know. But you can see that this is really an iconic World Heritage Site. And I'm going to show you something. So basically, we're going to look at shallow water type equations and finite element method. We're going to have somebody beating a drum. We're going to have somebody beating a drum in the middle here. And we're treating air as a shallow water. And Tristan Pryor did the simulation I'm going to show you. We have weak conservation of linear angular momentum, and we have exact energy conservation using an analog of a trick called the discrete gradient method. And he was able to build in exact energy conservation like that. So what do we do? Well, I read this book. I read this book by a guy called Anthony Johnson, which kind of I thought was totally wonderful. And the book shows that makes the case that this is the precise survey of those stones in Stonehenge. So because you have to do it using only ropes and pegs, and using ropes and pegs you can divide your circle into 30, and you can count them, and you can draw these circles and these intersections and put so this is your arch of stones at these points. And the whole book, apart from the 10 pages of mathematics to get to that point, is the proof, digging through the archaeological records and the sonic data and the this and the that to prove that actually this is where the stones were to so many significant places. Yeah, so that's what it is. So that is the mesh, and I'm now going to show you the video. No, come on. And I'll play it a couple of times so that you can see what's... No, it doesn't want to do... Okay, well, let's just start it again. So we just have a drum beating. We have a drum beating, and if I stop it at some point... Oh no, come back. I just think this is wonderful, you know. I mean, maybe I'm easily pleased. But what we have is circular sound waves coming out and being refocused, and to form some kind of a sonic torch, and that heads off down the avenue. So, you know, I mean, we can speculate and have fun, and maybe you need like 5 drums and 3 trumpets.
Is that with a loudspeaker?
Yeah, I have to wonder, because you see, the reason I wanted to do this is because of those intersecting circles really look to me like some kind of diffraction grating or something like that. I mean, my physics isn't brilliant, but I wanted to try the experiment. And of course, you can't go there. You can't do it because first of all, they won't let you there, and secondly, the stones, some of them are on the ground, so you can't actually do it. You can only do these simulations. But the fact that we had a very precise survey of where those stones were kind of gave added impetus to having a good time. I mean, the whole point is to have a good time, right? Okay. Tools, what am I doing? How do I see the whole thing? View. Alrighty. So there we go, a sonic torch heading off down the avenue. Alrighty. So I've also got an extension of the smooth Noether second theorem, which I did with Peter Hyland, who also worked with me on the difference Noether's law. And there's a drop dead gorgeous trick in the middle of this that makes it work for finite difference. And with the so which is really was very pleasing to me. And then the second thing is that I do have written out a proof that you can conserve potential vorticity using the result I proved with Tristan. So potential vorticity, so in other words, you give me a Lagrangian which is invariant under area preserving diffeomorphisms of the plane. So that's some shallow water equations and quasi-geostrophic equations. They will, so I did show theoretically that you can conserve potential vorticity in the sense in which I prove in the theorem, but that's not been numerically tested. But the proof is there for anybody who's interested. I haven't published that. It's just just on the archive somewhere. I need to put it on the archive somewhere. Anyway, thank you very much for coming. Questions? Robert.
So this method where you preserve a symmetry by making the grid points into dependent variables.
Yeah, oh, that's the standard trick for, yes.
That means their motion is now determined by the variational equations. So do those grid points move in in a nice way.
No, it's ugly. So what you want to do is put in some Lagrange multipliers to keep them all constant and dump the variation onto the Lagrange multiplier.
Again, sorry?
They're ugly. I don't like them at all. They lead to very nonlinear things, and so, that's why we've been making them, constraining them with Lagrange multipliers, and putting the complexity onto the Lagrange multiplier, and that does help for some problems.
Still preserves the symmetry, the conservation law.
Oh yes, so you then induce an action on your Lagrange multiplier to preserve the symmetry, and you can do that. Yes, yes, you can do that quite a lot. Yes, I mean if all you care about is it depends on what you want, but again, if the as long as it's not too elaborate, you can, provided that difference, provided the difference is a relative invariant, doesn't itself have to be invariant, it can be a relative invariant, then you can create an action on the Lagrange multiplier which will preserve invariance. It means your conservation laws involve your Lagrange multipliers, but that's the price you pay. Yeah. Yeah. Yeah, Ari.
So you mentioned briefly looking at finite element methods, and you said that there was sort of a weak version of a conservation law.
Integrals over sums of integrals and jump terms.
What methods and what equations were you looking at? Like a simple test problem that you were.
Yeah, the simple test problem was a P Laplacian on the plane, and the test and it was the proof of the weak form of angular momentum, and Tristan found superconvergence to the smooth law. It's detailed quite heavily in the paper, in that paper with him, the test problem. Yeah. But you really need to talk to Tristan about anything with Sobolev. Yes. I can understand it, but I'm not that fluent that I would be that confident. Yeah.
All right.
Yeah.